One thing I wanted to note was, usually at real talks, if we were live, we could chat at the end. I hear that there are maybe students in the audience. I'm happy to hang out after the talk is done. If anybody wants to talk about career stuff or has any other like lingering questions once the main talk is done, if you guys support that, I'm happy to hang out. So one comment on that front, and then questions. So I'm happy to do Q&A live kind of during the talk. So whenever you guys want, just feel free to unmute yourself and ask a question during the presentation. And we can just deal with it then. We'll try to get this done in an hour. If there's a lot of questions, I might kind of then ask to beg off a little bit just so we can get it done and not hold people for too long. But otherwise, back and forth during the chat will be perfect. So as Jerry mentioned, right, one of the thing I wanted to talk about today with you folks is a little bit of climate change, and specifically kind of this climate intelligence domain that NASA and other space agencies, to operate in. And one of the things we focus on is what's happening to our planet now and help the rest of the climate community figure out what might happen in the future. And specifically, right, our role is generating, planning current and future space-based observations and also supporting modeling efforts. So we'll be talking about those things. Okay, actually, so one thing I wanted to highlight, and I think you guys are all, scientists for the most part, or, geologists or environmental science, et cetera. So I don't think this is a surprise to you, but I think this is kind of a fun picture because for a couple of reasons, right? One, it's showing Earth at night from the space station, so it's just kind of cool. But maybe more interestingly, I think a lot of times people have trouble kind of just internalizing the fact that we are changing the planet, and this kind of highlights a few of these items, right? One, there are tons of people, as you can see, right? This is obviously the Nile River Delta, right? So you can see Nile River Delta and Cairo here. So lots of people having a visible impact on what the Earth looks like from outer space. And the other thing that's highlighted here is the atmosphere, as this very kind of almost paper thin layer between the solid Earth and space that keeps us all alive. And so there's not much of it there, even though it feels like a lot. So the fact that we're, pumping a bunch of different gases and things like that, into the atmosphere, you can actually change the composition, right? It's not kind of crazy to think that we can change the composition when you look at it in this relatively fragile, state that we can see here. So kind of a fun shot from that perspective. Okay, so contents of the talk, I'm going to hit, why do we care? I think you guys probably know, but we'll touch just the high level motivations. Then go into how we know what we know about climate, specifically a space-based view, so both current and planned observation system, and then a little bit of existing models, and then touch on using those techniques, the observations and the models, what are they telling us about climate? So mostly hitting some of the highlights from the IPCC AR6, the assessment report number 6 that just came out, working group 1. Using some of those kind of graphics to talk about what we know. And as Jerry said, then hitting on, what are the big residual uncertainties, and at least on the space agency side, what are we trying to do? And so even though I'm talking about a lot of space agency things here, a couple of disclaimers, right? One is I am not representing the views of NASA and JPL today in this talk. So I'm trying to maybe be a little bit more blunt in a few places. And also, as you heard from Jerry, I'm an engineer by training. I am not a climate scientist. So some of the climate stuff here is a little bit more by osmosis over years of working with smart folks. Feel free to ask questions, but sometimes I might not have all the answers. But go ahead and poke. Okay, so why do we care, right? Some of the key framing motivations for Earth system science are dealing with climate change. Specifically, the fact that, it looks like we have some unprecedented challenges coming our way, right? Based on what we think we are doing to the planet and what the likely consequences are. And so that requires really unprecedented foresight to understand how to best mitigate those issues, try to minimize the bad things that can happen, and then just kind of deal with, predict or project, and then be ready to adapt to the changes that are coming our way. Right? That's a key objective. So what's going on, how and why is it happening, trying to answer these questions. What could and will happen in the future, which then really influences what actions should we take and how might our actions impact that future, right? And these things all require a deep understanding of, of the planet, the atmosphere, what humanity is doing to it, right? And to get that understanding, you need to look with sensors and things like that. And so using that background, right, and those kind of capabilities, figuring out what are the most effective actions to achieve the future we want. So this is really part of the climate intelligence game, right, that we're in, and we'll talk about the tools that we use to deal in that world. And one of the big kind of, I guess, things that has changed over the last few decades, right? Earth science has kind of gone from more, hey, let's just figure out these cool things about the Earth and how it works, from a mostly curiosity perspective, right, decades ago, to now, hey, we probably have to make some really important decisions for society and maybe decide how we're going to invest billions or trillions of dollars over the next decades. Decision makers look like they need to be making decisions like that. And those decision makers are all the way from private citizens like us right here to corporate boards or CEOs to governments at local to national and international levels, right? So trying to provide the information to make the best decisions is a key objective that is becoming more and more the forefront of the world's space agencies. So that's the motivation, right? So a little bit of how we know what we know, and just want to give you guys a sense, in case you're not familiar, right, with the space efforts of all the different, the key, contributors on the planet, what we are doing, right, the scale of the observations we're trying to put in place. So this first picture is a view of the European Space Agency. So ESA is the European Space Agency / EU, which is the European Union fleet, right? And they are currently probably one of the best organized entities in the space-based observation game. And you see three threads here, right? There's a science-centric thread, so a bunch of spacecraft spanning from 2010 all the way to plans through 2030 that are trying to mostly answer maybe like process questions or one-off questions of, hey, how does this part of the planet work? Like Helios here is an example of a sensor that's actually measuring using a LiDAR, measuring kind of 2.5D wind speeds over the land surfaces of the Earth. So substantially science and research-based thrust here on this, and ESA's in charge of that. Right, you can see substantial, again, kind of every few years they're launching spacecraft, sometimes more than one a year. Then this middle thrust is kind of new. This didn't really exist. The Copernicus program kind of was spawned roughly, I want to say like late 2000s, early 2010 timeframe, and really got underway by mid 2015 and on, right? And this is kind of a new system that is focused on operational, i.e. like permanent observations of key variables in the Earth system, so surface, vegetation, ocean state, sea ice cover, et cetera, different things like that, but committing to doing those observations effectively kind of forever, right? So, similar to what we do in the meteorology world, right? So since the space program started, meteorology, right? So the National Weather Service in the US and EUMETSAT in Europe, others have kind of committed to monitoring the weather and trying to get better and better at predicting the weather, for decades now, right? But this kind of committing to monitoring the rest of the planet, all the other key variables, is this kind of new thing that Europe has really committed to, kind of in an avant-garde way, ahead of other players. And again, here we are today, right, in this roughly 2021 timeframe. You can kind of see the spacecraft that are flying and what's, the committed fleet that Europe's already kind of put money down, plans down for to fly. And these include things like L-band synthetic aperture radars, that's ROSE-L spacecraft, things like CHIME, which I'll talk about a little bit later. This is a hyperspectral imager from orbit, that we're trying to get like 8 days or less repeat coverage. So kind of Landsat on steroids. and also LSTM, land surface temperature mission. So this is thermal infrared kind of information. So you can do evapotranspiration and things like that, and mineral identification and things. So again, trying to get like on 1 to 2 day repeats with these missions. So a lot of, pretty hardcore investment in operational and practical info that then people can build software systems around and feed information streams to farmers and all kinds of urban planners, all kinds of different decision makers, right, that Europeans are committing to. And if somebody's got a hot mic, I don't know if that's a question or just a little bit of background noise. Okay. So again, the counterparts here, NASA kind of does the science side, and I'll show that in a second for the US. USGS, so the US Geological Survey, right, which operates Landsat, is kind of the one spacecraft line that we have that is, operational Earth observation, not weather. Right now we only have one of those, and NOAA obviously does the weather side here on the meteorology side, right? So one of the important things we've learned from the user community, including the weather folks, is for folks to really commit to using Earth observation data, you kind of have to tell them the data is going to be there for a very long time. And one thing the science spacecraft don't have is that commitment that they're going to keep flying these sensors kind of forever, right? Versus the things in the middle column, the governments of Europe are kind of committing, we're going to fly these forever, and you can invest in figuring out how to use this kind of data. So that's really a big difference. Just like the US community is committed, Geological Survey is committed to flying Landsat forever. And, there's a huge user community in the US, obviously, probably including a lot of you folks that use that data, right? So this is the NASA version. And again, with maybe, you see some Landsats here, right? So we build Landsat and kind of hand it over to USGS to operate it. Same thing with some of the weather satellites. We actually build those for NOAA and then hand them over. But everything else here is a science spacecraft, and there's no promise that there will be a second flight, right? So you might get 3 years or 5 years or 10 years of data, and then it might disappear. So users, often don't commit to internalizing that data for long-term applications. So that's one of the issues we're kind of trying to fix long-term with NASA and the US government. But pretty large fleet, right? What you see, and then this is NOAA. The NOAA fleet here, and you can see that we have both polar orbiters, so low Earth orbit spacecraft, that are doing that feed the weather models. NOAA also flies Jason-3, which is an ocean altimeter, and it does just sea level rise monitoring. Though NASA is kind of taking that back over with some spacecraft with the Europeans, and then the geosynchronous orbit we have goes east, goes west, and 2 spares, right, to make sure that if any of these go down, there's already on orbit spares that can jump in and provide that data set, in case there's a problem. So this is kind of the bulk of the Earth observing fleet, right? And all of these spacecraft that you just saw, they provide, again, tons of data that are fed into IPCC assessments and other things about what's happening to the planet. Now in some cases decades long data records, that have really been useful for understanding Earth. So then there's other government stuff I'm not talking about, right? The Japanese, the Chinese have a huge program, and didn't want to spend forever talking about these things, but more governments are doing things, but those data sets I just showed, those spacecraft kind of provide the vast majority of the data that's readily available, kind of freely available to the public, whoever wants to invest some time in figuring out how to use it. On the private side, there's been a huge change from kind of 2000 and before, where almost all optical remote sensing of planet Earth was government based, Landsat for the civil side and 3-letter agencies, right, for the intelligence community side. SPOT kind of started breaking that mold. SPOT was a public-private venture between the French Space Agency and French private entity, and started kind of selling commercial remote sensing data. And from roughly mid 2000s on, the private scene has really exploded, right? It turns out there's a huge market for optical remote sensing data, and now there's companies that are actually vertically integrated that build the spacecraft, put the sensors up have the software to analyze the data, and then we'll sell you geospatial intelligence products, where you can track ships around, or you can track what's happening to your farm, or, all kinds of stuff. News agencies will kind of show if something blew up somewhere, right? Like the before and after shot, maybe with some of these commercial remote sensing spacecraft. Your Google, a lot of the map satellite imagery, right, is obviously from these private entities. And so these days, probably, more than 90% of optical Earth remote sensing is done by the private sector, and government and private entities just buy the data from them, right? So that's kind of this new era. You can see this is a little bit old now, but this is from the European Space Agency, from their database back in 2017, that was kind of showing, total number of launches per year for spacecraft, excluding, larger than 50 kilos, excluding meteorology, right? So this is more traditional Earth remote sensing, not weather. And again, kind of annual launch rates, so between 2007, 2018, a total of around 220 launches. And now with some of these companies like Planet Labs, Rapid Eye Planetscope, they operate, functioning like 100+ spacecraft in orbit just by themselves. And other companies are putting up, sometimes handfuls to dozens of their own vehicles, right? And so there's now more than 500 planned launches through 2022 from the private and commercial and civil space sector. So this kind of huge explosion, because there is money to be made. People want the data. And here's kind of a smattering of those companies that some of you guys are probably familiar with. Planet, Maxar. So Planet and Maxar are probably two of the big optical companies. There's also now Capella Space and ISI that are deploying synthetic aperture radar, so all-day imaging capability using radar into orbit as well. So they're expanding out into different domains. So that's kind of a summary of the space-based observation world. I don't know if there's any questions on that so far. Nope. Okay. Okay, so models. I was kind of hoping to do a better synthesis here. The modeling world is large and has a lot of players and is hard to boil down. So there's only a few slides here. So again, the other side, besides just taking the data, right? We then take the data and often will feed the data into models for things like weather, right? To make these awesome predictions that we have now, like 7-day plus reasonably reliable weather predicts, right? But there's also other models, beyond weather models, that are looking at the state of many other elements of the Earth system. And so here you just kind of see a summary here, 4 major quadrants, right? Atmospheric models, different kinds, right, that are looking at different things. I'm not going to read all these out. Land models, right, that are focusing on things like hydrology, biogeochemistry, vegetation, blah, blah, blah. Cryosphere, this is a big deal, especially for sea level rise, but also other like shipping, northern countries like Russia and Northern Europe definitely cares about, for example, where they operationally monitor sea ice state so that they can help guide shipping traffic in the Arctic Circle and things like that. And then ocean, we have a lot of things going on in the ocean that people want to keep track of. So there's this slew, right? Large number of models that exist. I think, probably you guys have been exposed to like what a basic climate model looks like, right? These are typically gridded models with some lat-long resolution. Used to be kind of measured in degrees of lat-long. These days they are starting to go into kilometer scale, maybe 10, 5, now few kilometer scale, small, finer and finer resolution. There's vertical resolution as well, right? Both in ocean models and in atmospheric models. And today, still a lot of, because the grids are still relatively large, even if it's a few kilometers, there's a lot of physics that is kind of happening. The important stuff happens at finer than grid scale resolution. And so some of the things are parameterized and then kind of calibrated or tuned to make sure that the simplified parameterized representation of the physics is actually reasonably accurate, right? That gets done in the weather models and climate models as well. They show some of that info. So a couple things to be aware of, right? in case you guys haven't heard this, right, I think most of us know all models are wrong. Some of them are useful. It's an important thing to keep in mind. And we'll talk about that with some of the things we need to fix on the modeling side, back end of the talk. The climate community, as well as everybody else, whether you're an engineer or weather person or climate scientist, right, you kind of keep both of these things in mind, and we all make sure to design the model to answer the specific question that we have, test it for that question, and help make sure we understand the strengths and weaknesses, right, so that we're using it the right way and apply the appropriate uncertainties and stuff on that. And just a reminder, unlike weather models, which are literally trying to tell you what's going on tomorrow at hour X, climate models they're kind of tuned or optimized for looking at average conditions and how they're changing over time, over either the globe or regions. And so different intent. So they get maybe some different decisions made on how some of the coding is done or some of the optimization is done. And this chart just kind of gives you a feel for the complexity and maturity, how sophisticated the models used to be versus what they are today, right? So it's just kind of showing, so across the top here, you see time, mid 70s to, this is from IPCC AR5, so, which came out early 2010s, right? So, but the same trend is basically continuing, right? You can see how more and more components are getting added, right? So right now, we cover everything from atmosphere all the way down to atmospheric chemistry, and pretty much everything in between. But there are still missing elements. And actually, sorry, the other trend that's going on, as you guys all know from your computer, even just your personal computer experience, if nothing else, right? Moore's law has been wonderful. And so the increase in computing power that's happened, think about the 70s, right? Where, your iPhone, the computing power of your iPhone would probably fill half your house, literally. To today, right, that there's been a huge leap. And so that has actually allowed us to go from, again, these like very crude spatial and temporal resolution models to much higher spatial and temporal resolution models, which has been really important to get some of the physics down. But there are still things missing. So surface hydrology, especially subsurface hydrology, there are standalone models that do that reasonably well, but not necessarily integrated into the Earth system models, right? Climate models. Same thing for the cryosphere. The ice sheets and mountain glaciers typically are not included in a high quality physics sense in these Earth system models that people use to run projections of what's going to happen in the next 50 to 100 years. So those are kind of some of the weaknesses that we know about and are working to fix in the future. So using all of that stuff, both these models and the fleet of spacecraft, right? These dozens and dozens of vehicles that are orbiting the Earth and taking data, we paint the following picture, right, of kind of what's happening with the climate. So I apologize, those of you that have already kind of read, maybe on your own time, if you're into climate stuff, the AR6 results, IPCC, AR6, that I'm just going to show some plots, right, from that chat, from that report. So using both, modern observations from the satellite era, as well as in situ, thermometers from ages ago, or paleo records, right? You can see here kind of temperature, global average temperature going back the last 2,000 years, right? A lot of this is paleo records. You can see this kind of the trend, like what is happening in modern times versus what we have pretty high confidence happened global average, out here, right? So we're definitely seeing this big jump in temperature. And we've now kind of got models down where we can both use our climate models to say, okay, if humans were not around, like delete humanity, and all the fossil fuels and things we've spit into the atmosphere, what do we predict the temperature of the world would be, global mean temperature with just natural stuff going on, solar, volcanic, etc. And then if you put humanity back in, what happens, right? And so the brown line is simulated humanity back in, combined with nature, and you compare that to observed, and that kind of says, hey, look, we believe, all that climate model stuff I just showed you, apparently it's not completely useless. It seems like it's kind of explaining what's happening reasonably well, right? Because those models are showing kind of both of these, the not human and, minus humans and plus humans picture. So again, gives us confidence in the models and insight into the uncertainty. Other things that are reported on, so we just talked about these temperatures. right? So this is kind of to modern day. And then we use those same kinds of models to then project, okay, if we keep doing things, right? So this goes back to the decision support, what should we be doing as society? How hard should we be trying to mitigate things, right? We use those same models with different scenarios of how much emissions we might put in the atmosphere to then try to predict what do we think global mean temperatures might be, right, under these scenarios. So SSP are the new scenarios that are used by the IPCC group. And that shows kind of the projections, I should say, for global mean temperature, for Arctic sea ice cover, right, including projections for when we might kind of have practically ice-free, North Pole, ocean pH, right? If you're a fisher or somebody who cares a lot about what's going on in the ocean, this stuff kind of matters, right? Understanding, when coral reefs start having problems, etc. And then also sea level change. And here, this is kind of a sea level change projection for both through 2100, right? And then because there's a lot of inertia in the system, right? Sea level keeps growing, and some people have to make decisions. Some of the sea level related decisions are more, 100-year plus timescales. Like, hey, if I'm going to put a sewage plant somewhere or a nuclear power plant or some other power plant that I think is maybe a 50-year investment, or maybe for a sewage plant, it might literally be like a forever investment, right? That city might have that plant in a location and just keep maintaining it and fixing it almost forever. And so where do you site that plant if you're putting a new one down? You probably want to look beyond just the next few decades. You probably might want to look to the end of the century or even beyond that to kind of make sure, okay, if I don't want to get hosed by potential long-term sea level, where do I need to go as far as how high above current sea level? So that's what these different projections kind of show. Any questions on that stuff? Nope. Okay. And again, here you get a sense for, both predicted warming and simulated, and observed warming. So this is starting to give you a feel for like how much skill do we have, right? So you kind of focus your attention on this middle chart. This is actual observed, right? So from those satellites and the network of all the temp sensors that we have, on the ground around the world, reconstructed global temperature, today in this, we're roughly 1 degree C warmer than pre-industrial time, right? 1850 to 1900. And if you just kind of compare, like blink these in your eye, you can see, they're not perfectly correlated, right? This is the simulated, run a climate model that starts in 1850 to 1900 and run it forward to today. What does it say would happen, right? And you can see there's like, some broad things. Hey, look, the North Pole is definitely warmer than the rest of the planet, right? It was warming up faster. Maybe not quite as fast as the models say, but definitely warming up faster. This North Atlantic region is a little bit cooler. It's not like blue here, but it is a little bit cooler, right? Africa definitely a little bit warmer. The ocean's kind of missed, but again, like some of the trends in Africa are hit. Australia, same thing, a little bit pinker or whatever, a little bit warmer, right? That kind of agrees. So anyway, you can kind of see, there, if you kind of blur your eyes, right, there's significant correlation there. So again, we definitely believe like global mean, and yeah, maybe continent scale, is beginning to have some skill in making reasonable projections. And then this just takes that, warmer and warmer, right? So you kind of try to calibrate like how much you believe the details up here, and then when you're looking down here. So a little bit more of, again, details like what have we learned from observations. So these next few charts are similar when you see these little, like they almost look like war game hex maps, right? This is a very crude representation of the surface of the Earth, right? North America here, Central America, South America, Africa, Eurasia, and Australia, and New Zealand, etc. So what these are trying to show is, since from roughly 1950 to the modern era, 2020 or so, what have we seen as far as changes in heavy precipitation? And so again, there are two pieces of info in these plots. One, the color stuff is basically, is it increasing or decreasing, with like reasonable confidence? And the gray is either there's, maybe there's decent data, but not good agreement, right, on the trend. Is it actually increasing or decreasing, or kind of like, we don't know, not sure yet. And then the solid gray here is limited data, or maybe limited literature. So literally don't know, like not enough data. And so you can kind of make out, hey, parts of North America, Eurasia, definitely getting substantially more rain, right, over the last 50 years. So there's a trend, right, that's being claimed here. The second piece of information is confidence based on our modeling and observations that the human contribution, right, anthropomorphic forcing is actually driving this, right? So greenhouse gases, et cetera. And this is a little bit of a different story, right? There's not, you can kind of see the only high and mediums I circled here, Central North America and Northern Europe. Everything else is either a single black dot or single white dot. We're not, either kind of ambiguous because the models don't agree, or the observations, it's kind of on the fence, or just not enough data. Maybe that part of the world just hasn't had enough data yet to make a determination. So more confidence that something is changing than that it's human driven, except for a few places, right? From a regional distribution perspective, not global mean, right? Difference there. And then this is predictions in the future. So again, keeping in mind, here's what we saw. What are the predictions for the future? So you see some trends here, and I'm not going to take the time, but you kind of blink these back and forth and get a rough feel for, are we actually starting to see some of this? And to first order some of the Northern Europe stuff, yeah, look, you can see Northern Europe is turning, a little bit greener, right? So it is increasing. And looks like in some of these other scenarios is increasing more. These other like really dark green, some of these dark green places are because, like, for Northern Africa, you guys know, right, this is roughly the southern edge of the Sahara Desert. It's pretty dry right now. And so only a small change in absolute mean precip will have a huge kind of percent change relative to today, right? But there is this kind of greening of North Africa that might happen under climate change scenarios versus other parts of the world. South Africa drying out, Australia generally drying out more, the Southwest US, Central America drying out more. And then similar plot for drought conditions, again, showing like what can we say are reasonable confidence observations of increases, right, in drought conditions around the world versus where do we have maybe a little bit more confidence that it's probably human driven, right? And that's really, there's no highs here, only two mediums. So Western US and the Mediterranean, the climate community is kind of saying, hey, we think the increased droughts being seen in those areas are probably driven by climate change, at least to some level. And these other areas may be more natural variability. And then soil moisture is kind of the analog, right? This is predicted soil moisture. Now it's taking into account both precipitation, but also evapotranspiration and things like that. It's kind of an integrated product where you can kind of get a feel for overall, given both increases in temperature and maybe rain changes, what's the kind of integrated effect. These plots kind of show that. Again, North Africa kind of getting, relatively speaking, right? These are standard deviations. Relative today, getting, wetter as things warm up, and other places maybe getting a decent amount drier, especially if you don't, these kind of unmitigated climate change in the next 100 years, if you kind of do business as usual, you're looking at these 4 degrees Celsius scenarios, things getting substantially drier, right? So places not to be a farmer. Anyway, so that's kind of, top level summary of observation models and what they have been able to tell us, right? And why people, why we trust some of the things they're saying, and why, there's kind of a significant clamor to go do something about it, right? We probably want to avoid the worlds that are this different from today because of the kind of repercussions for social and economic and other parts of the human fabric. Any questions on that stuff?
Yeah, I have a question, Daniel. Are you confident that, or not you personally, but are modelers confident that they have identified the key input variables? You mentioned two areas that need to be incorporated into climate models, but are there other issues or technical variables that nobody may be even aware of?
So I'll talk about that. That's a great question. And I will definitely, so I kind of hinted at that a little bit, but I actually have like a little section that talks about that more specifically. And yeah, the preview is, we know there's computational issues. We know there's probably, some processes that aren't well represented that we need to do a better job representing once we have the computing, and other capabilities. But that's, we'll get to that. So I'll hit that.
And then I had a kind of a follow-up on that one. Mm-hmm. Are there any of these variables that make the models, or let me turn around. Are the models extremely sensitive to any of the variables, such as that if you change them even a small amount, they can have a huge impact on predictions and many years in the future?
That's a great question. So I've done those kinds of sensitivity runs
like with butterfly
models.
That sort of
the what?
The butterfly, the flapping wings of a butterfly.
Right, and so I think there are some that we worry about, right? So one of the things that the community does is try to identify tipping points. So maybe it's a little different than what right? So we do worry about tipping, are there tipping points in the climate system where once you exceed some threshold, you go from a currently stable state to maybe a rapidly changing transition and then some new state, and then it's really hard to get out of that new state, right? Mm-hmm. So that people are trying to identify and maybe give warning of like, hey, are there places where we're reaching or exceeding tipping points? But I think you're poking at something else, which is, have we done the sensitivity runs to say, hey, if we screwed up our estimate of this thing, right, this variable, which ones have the biggest impact? And
yeah,
I think the one that comes to mind kind of most obviously is the cloud feedback, right? So there's this, generalized, I forget if I have it in the charts. We call it the temperature climate response function. And so transient climate response to cumulative emissions, right? So this is kind of based on greenhouse gas, like how we know the greenhouse effect works, right? That's the basic math. That's why this is a positive slope, like temperature change, temperature increases with cumulative CO2 because effectively you're putting a thicker and thicker piece of glass, right? Greenhouse gas glass over the earth. But then there's feedbacks in here that change the effective rate. Like, hey, is the albedo of the earth increasing or decreasing, right? Things like that. Like, are there more clouds? And the fact that there's more clouds because the air is wetter, going to reflect more light out, right? So that biggest single unknown is kind of what the clouds do with albedo. And that is still, we don't, so people have a range of estimates based on different calculations of what that feedback is. And that definitely is probably the single biggest swinger. And different models have different flavors, like effectively versions of that variable, right? Effectively that you can pick off. Some of them have it a little bit on the high side, like, if you double the amount of climate CO2, do you only, you might get 3 to 4 degrees of warming versus other models might only get 2 degrees of warming if you double the amount of CO2 or something, right? Roughly.
Okay, thanks.
Yeah, that's good question. So it's still a little bit up in the air. Okay, so now I'm going to jump into the residual uncertainties. Right, so just touch on some of them, and some of the plans to reduce the known uncertainties. And if you guys remember, right, so the science world and engineering world has definitely talked about known unknowns for a long time. Those of you that aren't, maybe 20, right, if you're around during the Rumsfeld era, I think he made this famous by talking about known unknowns and unknown unknowns, right? So what we're talking about here today is, what we know we don't know, right? So the known unknowns. And so of course there's always the risk that there's stuff that you don't know, the unknown unknowns that might have a significant effect and kind of completely screw over your predictions. But like by definition, you don't know what those are. But it's another reason to kind of be conservative, right? Like we're moving the Earth into a new state, and there probably are unknown unknowns that might surprise you in, maybe good ways, maybe bad ways, probably bad ways. So, kind of the cautionary principle says try to avoid that. Okay, so a couple things. The obvious, right, is when we're making projections, and so, what drives uncertainty, projections of the future, the biggest source of that uncertainty is what is humanity going to do? Like, are we going to just not do anything, just keep spewing, all the fossil fuels we can get our hands on into the atmosphere? Or are we going to take a hard right turn and try to minimize that tomorrow, right? So because of that uncertainty, like what's human civilization going to do? You really can't talk about predictions, right? Because you kind of have no idea. To make a prediction, you actually have to have some odds. Like, hey, the odds are 5 and 10 out of 10 that it's going to go a certain way. It's kind of fundamentally unknown right now because our friends in the social scientists haven't figured out, and the social sciences haven't figured out a way to kind of predict human behavior with any kind of real confidence. So we talk about projections generally when we look forward, not predictions. Predictions are more like weeks to seasonal. You might have predictions. Once you talk climate, years, decades, centuries, you're talking projections. Okay, but having said that, right, even though there is that big uncertainty, there's still others, right, that are important for us to be able to do that kind of decision making and planning assessment. What should we do with our money? How hard should we put on the brakes, et cetera, right, for certain things that we're doing. And so those uncertainties we'll talk about here. Okay, so a couple of big picture items. This is a little bit supposed to be the forest view, right? So climate science, as I tried to explain earlier, right, climate science, the observations, the models, the analysis has basically settled the broad outlines of the problem, right? So there's no question that the mean temperature of the Earth is increasing, and that it's 99% likely, which is basically as confident as you'll get from a scientist, right, that it's humans. And so these more and more complex models continue to confirm what very simple models predicted decades ago, maybe even 100 years ago, right? So I mean, some of us can do greenhouse gas model, like super simple versions on a piece of paper, right? And you can come up with predictions. Hey, if you increase CO2, you're going to get warmer. And so, one of the concerns was, hey, maybe we're missing all of these feedbacks and it might change substantially the story. Well, it turns out the story isn't changing that much, right? Even as we add more and more complexity into the representation of the Earth system. And so the causes of warming, the trends, this global distribution of the impacts, that's all also settled, right? Approximate pace of what's going to happen, we think, is pretty well, again, approximate being the key word here, settled. So enough information to inform broad policy, right? So at a global scale, hey, humanity, if you want to stay around and not stress out too much about your existence, you probably should be mitigating emissions as soon as possible, right? So there's enough info here to make those kinds of recommendations. And that's what you've kind of seen the IPCC, that group, right, get more and more confident in asserting over the last couple of decades. Okay, next big picture item, right? So not settled is the fine scale stuff, what I was kind of also hinting at a little bit. So in the physics-based models, right, there really often is not enough resolution and confidence in regional and local scale projections. And so, like, for example, if you're thinking about where should I buy a house, to minimize my climate risk exposure, you will actually find papers that make some recommendations, but it's still kind of iffy. There's substantial uncertainty still there of like, is Georgia better than Tennessee, right? Or is Georgia better than Seattle, Washington? There are kind of a little bit more confidence on the regional scale of like the Southeast is probably not a happy place to be 100 years from now because it's going to be really hot and humid, Southeast US. But beyond those broad statements, you can't say maybe a lot with confidence. So then this hinders our ability to maybe be really smart about fine tuning or being elegant about how much adaptation measures to put in place. How fast should I build that seawall, right? If I'm on a coast where seawalls might be useful against sea level rise. Those questions are a little bit harder to answer. And the other thing to keep in mind is that, because of these resolution issues in the models, the magnitude and likelihood of extremes at regional scales is also not settled, right? And it's important to keep in mind, because of the limitations, we're probably underestimating the extremes. Like almost by definition, the models tend to smear things a little bit and kind of go more toward the average. And so their representation of kind of 3 sigma events are maybe not good. And those are really the ones that kick your butt, right? As I think most of us that have seen, for example, erosion happen, right? Like nothing erodes until, maybe for a decade, nothing happens in your local hiking canyon. Then you get some giant flash flood and, the canyon is like completely different, from yesterday. So these extreme events define a lot of the impact, and we're probably not estimating them well and probably underestimating. The other thing, so besides climate models, we also have integrated assessment models. So these are kind of joint climate plus economic, social models. And they, because of limitations in, our computing capabilities and just, fidelity of the models, they also they're generally not physics-based climate models. They're usually statistical, kind of like machine learning tuned to say, okay, look, we think we understand the first order relationship, like assume it's linear, whatever, approximate relationships between human forcing of the climate and the response. And so they often lack complex feedbacks, and especially in the human, like social, economic, different elements of the human sphere, how they interact. And so again, they probably also typically underestimate the risk that we have from climate change going, in the future. So this stuff is not settled, and we can definitely make improvements here. And there's actually people that are now starting to get some pretty sophisticated like network models. That's kind of a cool domain. Multi-layer network models and like representing society and different parts of society, like businesses and even physical infrastructure and human, actors in those network models. So those are starting to get kind of cool and been more and more capable all the time, but still just starting up. Okay, so this is, these 2 slides, it's kind of a nuanced story, right? Like, hey, look, we have confidence in the big picture, but our high resolution stuff still kind of sucks, and I'll come back to this later, in that it kind of influences the conversation a little bit, in that, it's not a simple story to tell. It can and is misused by people that may be in bad faith, right? That are on one side of the debate or the other. And it's also like, if you're trying to talk to politicians or something, people that are generally non-technical, it might be hard to kind of make the point of like, hey, we kind of get the big picture, but if you really want us to help you figure out if you should be building that sea level, protection wall, like 2 years from now or 15 years from now, we could use some extra investment, right, in better models and observations and stuff. So that it's a nuanced story that we are still learning how to kind of tell. Any questions on that stuff? Okay, move on. So some more specific gaps. So this is kind of, I think, where you were going, Jerry, right, a little bit. So some of the things we know, spatial and temporal resolution, right, are definitely issues in the models, and the computing power as well, right? So there are parts of the physical system of the Earth that we know perfectly well. So, governing equations of, fluids, right? But because of lack of available computing power, we're kind of stuck, especially in the past, right? We're stuck with these kind of very coarse, you can see a little bit in the background, coarse scale models versus fine scale models. So you might miss, like, certain physical things just don't happen, like small scale eddy circulation, which it turns out really drives a lot of the atmosphere ocean heat exchange and carbon exchange, and stuff like that, just completely don't even show up, right? Because your ocean model might not even turn on that circulation mode because it doesn't have enough resolution. So that used to be a bigger deal. It's slowly getting better. And again, we can kind of we can alleviate some of this with these like regional kind of zoomed in model runs, but it's tricky to feed that back into global model runs if you want to do 100-year, high, like you can't run regional models, all over the planet for 100 years and then like tie them back to a global model or something like that. It's kind of tricky. So we have that known weakness, right, that we're working on. And then there is process understanding where we literally don't have enough understanding of the physics of how something is happening. And it's either not represented in the model because, I guess this one is like literally we just don't understand the physics. So ignore the convection one. That's a bad example in this case. But cloud physics is real, right? Like we don't really we haven't observed enough clouds and like how, things go from like very humid to nucleating, droplets to other things to really represent that well in models, either both from a parameterized, like we have parameterizations of those, but maybe again, we have this wide range of people's guesstimates of how that works, which results in, again, this like factor of 2 variability in the climate sensitivity, temperature response to a given amount of greenhouse gas warming, right? So this is an area we know we want to fix, and we're actually, NASA and European Space Agency and others are trying to design radars and other observing systems to help kind of get at this better so we can improve our process understanding and then put it in the models. Okay, so that's 2 of them. And then there's also just, some parts of the natural system we've just started observing well, right? And we don't necessarily have good paleo records for, so there are places where we're still trying to untangle like what's reasonably natural variability versus new trend, right? That's part of why back here you kind of see these maybe not much high confidence yet, right? Even medium or high confidence in that humans are causing it. Like we can't disentangle. Is it just normal up and down, or is it the human, greenhouse gas forcing that's doing that stuff? So that's what this is talking about. Now, again, things like global mean temperature, actual, mixed total atmospheric greenhouse gas concentrations, sea level. So it turns out for a lot of decent things, for a lot of things, we have been able to generate paleo records, so looking at tree rings, looking at gas bubbles inside ice cores and other stuff to kind of make what we call proxy records that let us go back, past the age of thermometers and space-based remote sensing to create records and understand. So again, we have confidence that this temperature spike is real, right? The global mean temperature that you kind of see in the background here is real, and that it is really warmer than anything we've seen in thousands of years, right? And that it's being high confidence it's being driven by our fossil fuel emissions. But finer scale things, so like Antarctic ice shelf circulation, which kind of matters, like how fast might Antarctica melt on you, right? And the temperature and salinity profile in there, plant species distribution at high, at species level, and not just like, hey, was it savanna, not like ecosystem level, right? We don't necessarily, we have mixed records for, if you happen to find good fossils and stuff like that. Deep ocean circulation, and then other just under observed elements, right, that you don't have paleo records for. So for these things, we have a little trouble, right, with the variability versus new trend assessment. And right, so our solution going forward is to just have better sensors and try to make them persistent, at high resolution, temporal resolution, spatial resolution, and kind of, again, last forever, so that we can really start teasing apart variability versus human-caused issues better, right? So we know we need to do that. So again, this is just kind of an example, like one of my, I guess, more favorite examples from, this is IPCC AR4, where it kind of shows, they try to communicate roughly, in a cartoon sense, the spatial resolution of climate models from, IPCC Gen 1, right, 1990, all the way to back then, the 4th report in 2007, to kind of give a feel for how much better the models are getting, right? And that trend is continuing. Okay, any questions on that stuff?
I have a quick question. And this kind of goes back to, like, I think it was slide 23 or 22, with where it shows the full Earth, and then you can see the increased precipitation in the tropics and the subtropics. Yeah, there you go.
Yep.
Now, looking at this, what immediately comes to mind is that you have the convection cells, that something's happening to them, right? The Hadley cells and the what are the mid-latitude cells, and then you got the polar cells, which are
Right.
responsible for the trade winds. Are those being strengthened, or those being weakened by climate change? But they're obviously being affected in some way, and that's what I see here.
Yeah, so I mean, my roughly layman understanding, right? So those cells are substantially driven by energy imbalance, right? And so temperature imbalance, right? So we have a lot more energy hitting the equator, right, than the poles. And so a lot of this circulation, both ocean circulation and atmospheric circulation, is just trying to move heat from, you know, this kind of uphill high energy location to downhill low energy locations around the planet, and then all the funky ways that happens, right? And so one of the things that, you know, because the poles are warming more, right, because ice is melting, you know, that gradient, even though like overall the whole thing is warming, I think the gradient is decreasing a little bit, but I'm not actually 100% sure, right? But if the poles warm more, right, then at least that element of the gradient is decreasing and maybe messing with some of the strength of those drivers. And I don't know, maybe there's somebody else online that can actually probably answer it better than me.
Yeah, so what I've heard from other people is that, you know, these cells are actually weakening.
Right.
And I never quite understood it, but the way you explained it does make sense. If the gradient, temperature gradient is less, you know, then that makes sense. They would be weaker, which would have an effect on the trade winds,
Right.
and on the precipitation and the drying out of the subtropics, which would make sense why Southern California might get drier over time, and the tropics might get wetter over time.
Yeah. And Southern California, it's actually still, you know, the other thing that's maybe not represented well here is if you try to zoom in, even from these IPCC6 results, and try to get a reading of like, is California actually getting wetter or drier? It's kind of on the fence, right? A lot of us maybe care about this of like, hey, should I live here another 20 years? And I think the total annual precipitation is maybe barely changing. And there's like error bars plus or minus, like, is it going to go up a little bit or down a little bit? But I think the other thing to keep in mind that these particular plots aren't showing is we will probably get, even if we're still getting 10 inches a year, it might be like 2 storms, right? And you get 5 inches out of each of those 2 storms, and that's it. And so, you know, the extremes, how it's getting delivered are changing, and that also matters, right? So, yeah. Okay, I'm going to try to speed up here since we're getting close to the hour. So, given those gaps that we just talked about, right? How do we deal with those? So one of the things we do in the space business, we're getting better and better at is, you know, so we have historically built a bunch of spacecraft. This little figure on the bottom is kind of showing our process for developing, you know, new missions. We have used data from those missions to fill, you know, like, hey, what's actually happening, you know, in the Earth? And these are all just different, you know, flavors of the Earth system that we might care about, right? Highlighting atmosphere or ocean or whatever. And then over time, we're getting better and better understanding, right? So we take that knowledge, right, of observations, we build better and better models. And then we are interrogating those models to kind of do what Jerry was poking at, which is like, hey, if I care about sea level rise, if the thing I care about most, right, is what's uncertainty in sea level rise, let me mess with, you know, cryosphere models or Earth system models or whatever to understand which variable, you know, sea level rise might be the most sensitive to, right? And it turns out in that particular case, it's all about melting Antarctica. And so then you can say, all right, well, if it's most sensitive to that thing, are we already measuring it? And if not, then, hey, maybe that's low hanging fruit. I should go build a mission, right? Or do something, or build a submarine or whatever, right? To go interrogate that physical variable state so I can reduce my uncertainty, increase my understanding, et cetera, right? So that's the loop we are trying to more and more rigorously close, right? It used to just be like, we have no idea what's going on. Let's just go out there and take pictures, right? To, okay, now we kind of, especially for Earth, we really know what's going on. Like we've got petabytes and petabytes of data. We are getting more and more refined about what's the best question to ask and the best sensor to send up for the money spent to reduce, you know, to kind of have the effect you want. So, you know, JPL, Goddard, Europeans are all kind of getting better at this. Okay, so then a little bit of just jumping into what you know, using those techniques. What are we planning on doing? So I try to pick a few things that maybe you guys care about. So if you're kind of Landsat, you know, land surface imaging fans, there is a plethora of stuff coming downstream for you, right? So we've got global hyperspectral imaging and monitoring that right now we're doing with Landsat and Sentinel-2, I think. Right? And both Europe and NASA are committing to these hyperspectral imagers. So covering, optical all the way to near to the shortwave infrared, right? 380 to 2,500 nanometers in 10 nanometer bands. There are 3 spacecraft being planned between NASA and ESA, each one with a 16-day revisit. So you're going to get that data like every, 5 and some change days, right? So they have wide swaths. So we expect those launches to start in the 2020s. Same thing, thermal infrared. Right now, you just kind of have Landsat 8-9 and a little bit of Sentinel-2. They're 100-meter resolution. They only have 2 bands in the infrared, 16-day revisit for each spacecraft. And so between a bunch of players, the French Space Agency and the Indians working together, NASA, and also ESA Land Surface Temperature Mission, we're now building like a little flotilla. So, almost all of these are doing 3-day revisits. So we will be getting, once all these launch by the end of the decade, less, like 1-day revisit with the fleet or better, right? Which will be awesome. Like farmers around the world, we'll be able to do this, evapotranspiration and kind of really doing smart irrigation planning and stuff like that. So that's all good. And then similar for interferometric SAR, so we can build elevation maps, do elevation changes. So basically between the US and the Europeans, we're kind of committing to this kind of high resolution change detection stuff for, effectively forever, starting in the mid-decade. So that's all awesome news. And this just shows you a little bit of an example, kind of Landsat, multispectral, if you get like 8 channels or something like that, you can classify ecosystems, very broad, shrub, pasture, crop, right? Kind of stuff versus if you have a hyperspectral imager, closer to what we're planning to do with these new missions, you can kind of get down to the plant community level, and even though they might be the same spatial resolution, you can resolve a lot more just stuff correctly, right? You're seeing that on the picture on the left. And then because you have 16-day or 8 or 5-day revisit, right, you can trend this to see how your ecosystems are changing at, seasonal, sub-seasonal scales, and you do that for years and decades, you can really understand how, biodiversity is changing and stuff like that. So a lot of people are excited. This is just basically saying there's a ton of greenhouse gas monitoring missions that are going up, both a mix of government and even private sector missions. And then you can kind of see their launch dates here. So, and then also climate modeling. Sorry, I'm out of time here. Right, so this is a little bit messier, and this might just be I'm more of a hardware guy, right? I've spent more of my life kind of playing in the hardware world, so I know more what's going on over there. The modeling world seems a little bit trickier to understand, at least for me, right? So in the US alone, we have 6, I think maybe even more federally funded, like federal lab, NOAA, NASA labs, NCAR, et cetera, that are doing climate modeling, and even more than that at the university level. And for whatever reason, we seem to be pretty good at building big, complicated pieces of hardware, ever since Apollo and even the airplanes, right, and cars, from the turn of the last century. But we aren't as committed as a society to really do a super hardcore job developing these models, right? This has been left more still to kind of lab environment, I would say. Some of these are really rigorous, many of them are very rigorous now, but it's still different from like an engineering project where you stand up, you give people $1 billion, you stand up 1,000-person army and you go build a spacecraft, right? There's less of that going on in the modeling world. And so the funding is much, typically much lower than these big hardware projects that we put together for, making the measurements. Per that nuanced story that we talked about, there's a little bit of a PR issue of maybe not as clearly as possible advertising the needs to improve the models. Also the value of information might not be getting, like how important what you can do with better models might not be getting communicated. So we're kind of more in this slow but steady incremental improvement mode on the model side, which is I'm personally kind of bummed about. There are some exceptions to that. I think, this is getting recognized. There was a National Research Council report in 2012 to try to kind of shine a light on this a little bit. But it's still kind of slow going. And same thing with the IAMs, right? So those are also, they're making progress. There's some promising techniques, coming up, but it's relatively slow going, right? Compared to what I would say, if you did a Manhattan project or, really wanted to make progress here, I think you could go substantially faster. So quickly concluding remarks. Let's see, right? So, one of the messages we've, the space-based observations have been instrumental in understanding the current state of the planet and, helping feed the models that then, tell us what's going to happen in the future. And we've got a lot of planned observations, right? People are starting to get nervous about this. We've got a decent amount of observations, coming down the pipe that will fill, a decent amount of those known gaps. There are still other gaps that aren't getting addressed yet in the, kind of budgeted line items. And so there are still things that could use a little more money to close more of those gaps, right? But maybe more importantly, though, the climate model side, again, there's been a lot of progress. There's still a ways to go. And this area probably, like, bang for the buck wise, you could probably make more progress about getting smarter what the future holds by investing, like $1 spent in the modeling world, computing, supercomputing support, like making more supercomputers available to the climate modelers, maybe getting more software development talent into the game. Per $1 spent, you probably make a little bit more progress here into improving your understanding of what's going on than on the observation side, just per $1. Both are needed, right? But this area probably is a little bit lower hanging fruit in general, per my personal, takeaway observations, just kind of working in the field. So anyway, that's the main thing I had. Sorry, that was a little long.
Hey, I have another question for you.
Okay.
Geoengineering, is that taken seriously by the climate community, do you think? It's a pretty scary topic to me, but do you think that there's some credible research out there that might even be have promising results using your model technology?
Yeah, so that's a great question. It's super controversial. It is getting more and more attention. So for those of you that don't know, right, geoengineering, or what we now sometimes call climate intervention techniques, right? So I actually have a figure. That was just in case somebody asked that question. Figure. Unless I deleted it. Did I delete it? Okay. So there's kind of, focus on the bottom part here, right? So I think for many reasons we're not, don't have time to go into today, like stopping putting carbon into the atmosphere is kind of just the best thing to do. It's the lowest risk. And you have all these awesome side effects of you stop dying from bad air quality, right? And so this mitigation and adaptation path, like mitigation mostly being stop emitting, right, it really should be like goal number one. And of course, adaptation is, hey, we've already committed to a certain amount of warming. We need to be able to just like take those punches and not collapse as a society, right? Or as a city or as a village or whatever, right? Be able to adapt. But, this is a huge challenge as far as getting ourselves off fossil fuels, right? It's hard for developing countries. There's a lot of legitimate reasons that make this, challenging, including people, not people's jobs, et cetera, right? There's some real human issues here. And so there's more and more concern that we might need to do something else. Like if we're getting close to some of these tipping points, right? So this is kind of a concept shown here for, identify the tipping points in the climate system that you're worried about, try to put an early warning system in place, do as much mitigation as you can, do this kind of easy stuff like carbon removal, which is, again, super low risk, like, negative emission technologies, sucking the CO2 one way or other, either by growing more forests, right, natural ways, or unnatural ways, right, using some energy to do it. That's also low risk, but the geoengineering is typically more things like solar radiation management, right? Those are the scarier ones, like, hey, pretend to be a volcano, right? Like we know volcanoes, a giant volcanic eruption will cool the planet. And so should we, do something like that, like spew a bunch of reflective aerosols into the atmosphere to cool down the planet to avoid a tipping point that we really don't like, right? And only do it for a decade or something while you let this other stuff scale up, right? The mitigation and carbon, like low risk carbon removal stuff, so just to try to avoid this negative consequence tipping point. And so I think we are there are many of us that are trying to say, look, this is a very rational, sane system to put in place, right? And so you might, even though geoengineering might suck, right, relatively speaking, it might be way better than this tipping point you're trying to avoid. And so, pick the worst of two evils. And so in that world, you should be doing some research on basic solar radiation management, for example, just so you understand at least like the devil you're playing with a little more, right? So that if you think you have to let that genie out of the bottle to save you from the worst genie, right, you're a little bit smarter about it. So that's kind of the context where I think there are responsible conversations happening, but unfortunately it is like this third rail of climate science where a lot of people in the community just kind of feel like, if you say we can solve this problem with other tech, right, solar radiation management, which has all kinds of other issues, including it doesn't deal with acidification of the oceans. If you ever turn this off, you're like very quickly back in deep dookie, right? And so anyway, lots of negative things there. So if you tempt humanity with that tool, then people will get lazy with these top two rows, which are the important ones. That's kind of the nature of that conversation. But again, we're kind of hoping that you can have a rational conversation and develop some of the tools without committing to being an idiot and using them for no good reason, right? And so, I don't know, does that answer your question, Jerry?
Yeah.
Okay.
Thanks.
Yep. Okay. Any other questions for the bejesus out of everybody? I apologize if I did. But,
that's very good.
Okay. And again, so I'm happy if there are students around that want to ask about, career stuff or whatever, I'm happy to hang around. Otherwise, I'm happy to bail. So whatever you guys want to do.